Hello everyone. So in this lecture, I'm going to continue this to talk about and discuss the deformation of a fluid under a shear force P, and I want to define the definition of viscosity in this lecture based on this deformation and the shearing strain rate and also the shearing stress. Okay, so let's get started. So if you just recall, we talked about this deformation of a material under a shear force P, and we found that the shear stress and the area have this kind of relationship here in the material, because in order for the equilibrium of the forces, right? So for the sigma F to become 0, we need this to occur. And for a fluid, now I want to define something similar to find the shear stress versus the strain rate. And to do so, we define something based on the velocity gradient. Okay, so as you see here, the velocity of the fluid for a moving plate on the top and a fixed plate on the bottom, you see that the velocity is variable. At the top, the velocity equals to u, the velocity of the plate, and at the bottom, the velocity of the fluid, or like something like water, also equals to the velocity of the fixed plate, which is 0. Okay. And so if it changes linearly, we could write this relationship for the velocity, which is u equals to capital U time, which is a known parameter, times y over b, where b is the depth of this channel, say channel or these two plates. Okay, so as you see, a velocity gradient is developed, right? Because the velocities are different at different locations, so du over dy is going to be the velocity gradient here, right? The velocity, the gradient of the velocity with respect to the y coordinate or y direction, right? Okay. So in this case, where we have a linear change in the velocity, du over dy is going to be, this is the u function, right? So it's going to be the d of this function, u, capital U, which is a constant here, y over b of dy. So the derivative of this function, uy over b, with respect to y, and because u over b is constant, right? U, the capital U, and b are both constant. They are not going to vary. So I just can take it out of the derivative and then calculate the only remaining variable is going to be dy over dy. So this is surely is going to be 1, right? So it's equals to u over b. So this is the velocity gradient for this fluid. Okay. So I just want to note about this observation where the velocity here at this point is 0, right? Because it's on the fixed plate. So we call this a special term, which is called no slip condition. So I just want to define that. If you hear that, the observation that the fluid both gas and liquid, doesn't matter, right? Sticks to the solid boundary here. For example, the fixed bottom plate, the bottom fixed plate, yeah. Fixed plate is referred to as the no slip condition. So when we talk about no slip condition, we just mean this kind of condition where a fluid velocity is zero because we have a fixed plate or a solid boundary. It could be even like soil or even rocks or whatever, like the air movement over soil or over streets, all of them, we have this no slip condition. That means that the velocity at the surface for this type of fluids, where they are stick to kind of a fixed plate or a fixed boundary, a solid boundary, is going to be zero. Okay, so this was just a side note. Now let's get back to this problem again. So, say in a small time increment, delta t, okay, I want to investigate the behavior of this fluid in a small time increment like delta t. What's going to happen? The thing that is going to happen is that the fluid is going to move the top boundary, or the moving plate is going to move with a speed u, right? So I expect that the top boundary is going to move with u, and then times delta t over a small increment, in a small time increment, delta t. This is the distance it's gonna go, right? So it's gonna be, and we call this delta A, right? Over a small increment, time increment. As you know, u is what? The velocity is delta x over delta t, right? So if I want to find delta x, I just need to multiply u times delta t. So this is just a reminder that what I did here. So u times delta t is gonna be delta A, right? And this is what I have shown here. If you see it here, delta A is the distance that the fluid or the moving plate at the top goes at small time increment delta t, okay? So I can write it here. I will write it here. So delta A, let me write it here. Delta A is u delta t, okay? And then delta beta. So delta beta is this angle, right? It is this angle here. So this angle, I can write, because it's a small angle, say delta t is small, okay? It's around like much smaller than 1, okay? And because delta t is small, so I expect that delta beta is going to be also small, is much smaller than 1, right? It's a small angle. For example, say it is like delta t is 0.001 second, okay? It's a very small time increment, so the delta beta should be also very small. And because delta beta is small, I can approximate delta beta as its tangent. So tangent of delta beta equals to delta beta if delta beta is small, and that is something you should know from trigonometric relations. For any small angle like theta, if theta is less than, I think, 6 degree, then sine theta almost equals to theta, and also tangent theta almost equals to theta. And this is something from trigonometric relations that I don't want to detail, but this is we know from there. So this can be approximated as tangent beta, and so this one equals to the tangent of delta beta is what is delta A over B, right? This is the tangent of this angle, delta A, which is this one, over B, which is this one. Okay, so this is the relation that we have, and I'm going to write it down. So delta beta is almost approximately equal to tangent of beta, delta beta, which equals to delta A over B. Correct? So this is the relation we had here, and I had written it here. So I'm just gonna clean it. And so now we have these two relations. So I'm just gonna substitute delta A here, from here, and get delta beta. So delta beta is gonna be U delta T, which is delta A, over B. Okay. So this is this is what we can find, and then we define the rate of shearing strain, or gamma dot, as follows. So I'm going to define gamma, the shearing strain rate, dot, as the limit of delta beta over delta t as delta t goes to 0. So this is the shearing strain, right? We defined the delta beta as shearing strain, and the rate of that is going to be delta beta over delta t, right? So this is the definition. So this is what we define as the rate of shearing strain. There is nothing strange here. And then I'm going to find this gamma dot. What is going to be gamma dot? So gamma dot is going to be, from this relation here, I'm just going to substitute that. It's going to be limit of delta t goes to 0 of delta beta. So I'm just going to write it down, substitute it from here. Is going to be U delta T over B times delta T, which comes from here. So these two are going to cancel out, and thus the gamma dot is going to be U over B. And we knew that U over B was what? From here, was the velocity gradient with respect to y, right? here. This is y direction. So the velocity gradient with respect to y, and this is what we found here. Okay, so I'm just gonna substitute that. So this equals to du over dy right? So now I want to write the relationship between shearing stress and this shearing strain rate. Okay, something similar to solid in a solid phase. Okay, so let's say something physical. If you increase P, which is a force, okay, if you increase P force, you expect that the velocity U should also increase, correct? Is that correct? If you increase P, like if you pull this plate with a higher force, with a stronger force, then you expect that the velocity of the plate, the moving plate, should be also higher, correct? So, and if the velocity of this is higher, then you expect that the velocity gradient should be also higher. Why? Because if your velocity is low, like this is u, this is gonna be your first gradient, and if it is very high, this is gonna be your second gradient, right? So this theta 1, say, and this is theta 2. So theta 2 is greater than theta 1, right? And theta 2 kind of shows your gradient, right? Because we had it here. For a linear change, your gradient is going to be u over b. So now I want to write this to find a relation for between the shearing stress and shearing strain. So let's see. So these are something we all agree. If you increase force P, so if you increase that, we agree that you expect higher velocity. So U should increase. And if U increases, as you see here, then du over dy should also increase, correct? So if you increase P, we expect a higher velocity, or U, and because U is increased, so we expect a higher velocity gradient, or du over dy. So I'm just gonna write, and thus du over dy should increase. So P, or force, is what? P, or force, is this shear force is the shear stress times area, right? This is what we had here. This force is the shear stress of the fluid times the area. And area is constant, say for the area of the moving plate. So if you increase P, then we expect that the shear stress should also increase. Tau, or shear stress, should also increase. And we also know, based on this expectation here that I have written, du over dy, which is du over dy, which also we know equals to this strain rate, right? We know it from here, should also increase. So the shearing strain rate should also increase. And so now you see a relation, a proportional relation between tau and gamma dot, which is shear stress and shear strain rate, right? So in solids, you had a relation between shear stress and strain, right? Shearing strain. But in fluids, we have a relation between shear stress and shear strain rate, the rate of shearing rate, which is gamma dot. Okay. And so we can also say that tau is, because the shear strain rate equals to du over dy, is proportional to du over dy. Means that the shear stress is proportional to the velocity gradient. Okay. So this is a very important relationship in fluids. Now I know this proportionality, okay? I know that these two are proportional to each other, are proportional, right? Tau and dy over du over dy. And now I want to relate them to each other, write an equality using a constant, okay? So for common fluids like oil and water and air, the shear stress and shearing strain rate are linearly related. So this relationship is not necessarily linear, right? This relationship is not necessarily linear. We know that they have a relationship, and the relation is proportional. Like if you increase tau, we expect that your du over dy should also increase, right? So we know they are proportional to each other, but we don't know the exact relationship between them, right? So it could be linear relation or it could be nonlinear relation. So for some common fluids like oil and water and air, we know that this relation is linear. So we can write tau equals to a constant, we call it mu, times du over dy. Okay. And this is very important relation. Mu, what is mu? Mu is constant of proportionality for this relation. And we call it absolute viscosity or dynamic viscosity. Or simply, the viscosity of the fluid. So this is how we define the viscosity of the fluid. Okay? So the viscosity of the fluid mu is defined in this relation, where tau is the shear stress, du over dy is the velocity gradient, right? And mu is going to be the constant of proportionality of these two variables, which is simply the viscosity of the fluid, okay? So the actual value of mu depends on different things like the type of the fluid and also temperature. So the actual value of mu depends on the particular fluid for example, air or water, and temperature. So for example, if you change temperature in a fluid, this viscosity is going to be changed. Also, the viscosity of air is different than viscosity of water. For example, the viscosity of water, we expect it to be higher, right? And the viscosity of air should be lower. So let me summarize the whole thing by defining this type of fluids where we have a linear relation. So if you have this kind of shape where you have a linear relation between your velocity gradient and tau, or the shearing stress, then this type of fluids like oil, water, air, these are all called Newtonian fluids. We also have fluids that they don't have a linear relationship. They have a nonlinear relation between velocity gradient du over dy and tau, and those are called non-Newtonian fluids. So let me just define these. So Newtonian fluids, these are fluids for which the shearing stress tau is linearly related to the rate of shearing strain du over dy. For example, air and water. These are two Newtonian fluids. And likewise, non-Newtonian fluids are fluids for which tau and du over dy are related non-linearly. Some examples of non-Newtonian fluids are toothpaste or some plastics. So for example, toothpaste, if you insert a shearing stress, if you have a shearing stress, that shearing stress is not linearly related to the velocity gradient. And for example, you need to first, at the beginning, if you, for example, for a toothpaste, at the beginning, if you have something like a toothpaste here, say, and then you exert a shearing stress to that. If the shearing stress or the force is very small or weak, it's not going to move, right? So when tau is, say, less than tau 0, right? When tau is less than tau 0, then this toothpaste material is not going to move at all, right? So for this, then your du over dy, u is going to be always 0, right? So let me just write it down here. The velocity is going to be 0, so du over dy is going to be 0, right? But when tau is greater than a tau 0, specific force, like if you increase that force a little bit for a certain range, then it starts moving, right? So if this is a toothpaste, say, then it starts moving and changing its shape, right? So then u equals not to 0 and du over dy equals not to 0 too. So this relationship is not linear, right? The relation between tau and du over dy. Because if it was linear, it cannot be linear. Why? The reason is very clear. Because for tau 0, which is not 0, du over dy is 0. Correct? And so, this is not a Newtonian fluid. Right? You cannot write that relation between tau and du over dy. And so that is why we call the toothpaste as non-Newtonian, because you need to exert some force in order for it to start moving. But that's not like water. For water, once you exert any force, even very, very weak force, it's going to move. Why? Because it's a Newtonian fluid, because it has a linear relationship between velocity gradient and stress, shearing stress. So to show this better, I'm going to show it with this graph. So this graph is going to show, on the top you have shearing stress, and this is kind of familiar for you, especially if you had taken solid mechanics. And in this axis we have rate of shearing strain, and in solid mechanics you had shear strain here, but here we have rate of shearing strain, which is gamma dot, which equals to du over dy, right? If you see it here, gamma dot is just rate of shearing strain is just du over dy. So I'm just going to write it as du over dy. Okay. So for a Newtonian fluid like this one, tau equals to mu du over dy. So we have a linear relationship. So I'm just going to plot it here. maybe let me just plot it with this. So this is Newtonian fluid. Newtonian fluid. And this is gonna be mu. If this is 1, this is gonna be mu, right? Which is the slope of this, right? Because this is tau. And for a Newtonian fluid, we have tau equals to mu du over dy. Okay, so this is going to be, the slope of that is going to be viscosity, what we define as viscosity, the slope of shearing stress versus rate of shearing strain. Okay, but for a non-Newtonian fluid, this relationship between du over dy and tau is not necessarily linear. So for example, something like this is a non-Newtonian fluid. Or like a toothpaste is gonna start from here, so you need to add some shearing stress, and then it starts moving. So the diagram will start from here, and it could be nonlinear. Like I don't know the exact shape, but it could be like this or this, and we define different things for this. Non-Newtonian fluids, it has a very comprehensive field which will not investigate in this course. For non-Newtonian fluids, for example, it's called rheology for people who are interested in that. Rheology is the field who are mostly working with this non-Newtonian fluids. And in that field, a lot of these materials like toothpaste or some plastics, the behavior of those are comprehensively investigated. Some of them are thickening as you like add some shearing stress. Some of them just get thinner as you add shearing stress, right? So some of them would be like when you add shearing stress, then they stop changing, right? At some point they just stop changing, or so they keep continuously changing. So these are something you can Google those, find this kind of non-Newtonian fluids. I just wanted to define this. And but mostly we're going to work with Newtonian fluids in our course. And also another definition that could be useful is kinematic viscosity. So this was mu is dynamic viscosity, and kinematic viscosity is very simple. It's just defined based on the dynamic viscosity, okay? So I just write it down. It's just a definition that we are going to use later. So kinematic viscosity is actually shown as nu. In some problems, we might give you kinematic viscosity rather than dynamic viscosity. And it's simply the dynamic viscosity, or mu, or the simple viscosity, over the density, or rho, which has the unit or dimension of length square over time, or meters, the unit is meter square over second, which is a viscosity combined with density. Okay, So this was just a definition that you need to know later on. If we talk about kinematic viscosity, we mean the dynamic viscosity over density, okay? So in the next session, I'm gonna solve one example of this viscosity problem, shearing a shear stress and shear strain rate. And then after that, we are gonna start the second chapter, which is the fluid statics. So this was just an overview of what are different type of fluids and of the parameters that we are going to use in this course. So let me just have a brief overview of what we learned today. So we started with this deformation of a fluid under a shear pressure, a shear force, and then we defined this velocity gradient. We found that the velocity gradient d over dy, if it changes linearly, is gonna be u over b in this problem. And then we considered a small time increment delta t, and in that time we know that the top plate is going to move at u delta t, which is going to be delta a. We showed it as delta a. And then delta beta, because it's small, it can be approximated as tangent of beta, which is going to be delta a over b in our problem, right? So delta a over b in our problem. And then we used this and found that delta beta should be u delta t over delta b, over b, okay? And then we defined the rate of shearing strain, the gamma dot, as the limit of delta t goes to 0 of delta beta over delta t. And then if you substitute everything, you get that gamma dot is actually y over b. And y over b we found is du over dy. So the rate of shearing strain or shearing strain rate is nothing other than the velocity gradient du over dy. And then we found that, and we hypothesized and we showed that we expect as you increase the force, your u should increase, and thus your du over dy should also increase. Your velocity gradient should also increase. So tau is linearly is proportional to du over dy. And for some fluids like oil and water, air, this relationship is linear, so we can write tau equals to mu du over dy. And mu is just called absolute viscosity, dynamic viscosity, or simply the viscosity of the fluid. And then we define Newtonian and non-Newtonian fluids based on this relation between the shearing stress and shearing strain. If shearing stress is here, and this is the rate of shearing strain, du over dy, so if these two have linear relationship, we are going to call that fluid Newtonian, and tau equals to mu du over dy. And mu is a viscosity, depends on the type of fluid. So it's not like it's always like this, it can be different, right? These are also, this is for example also a Newtonian fluid, right? This is also a Newtonian fluid, but with different viscosity. So this one has a lower viscosity, right? If your viscosity is higher, like for water, this kind of things, it's going to be something like this, right? Because you need to add more force to get the same shearing strain rate, right? So this one has a higher viscosity. So these are all different type of Newtonian fluids if the relation is linear. But if the relation is nonlinear, like this one, we are going to have a non-Newtonian fluid, correct? So these are some fluids that we are not going to study in this course. It's for a field which is called rheology. It's mostly studied in material science, and this is some fluids like toothpaste or some other plastics. These are the ones that have this Newtonian behavior, okay? So our focus is on these Newtonian fluids in this course, where we have a linear relation between the shearing stress and rate of shearing strain. And then we define kinematic viscosity, which is simply the absolute viscosity or dynamic viscosity divided by density, which has the unit of meter square or a second. Okay. So as I said, in the next session, we are gonna solve one example of this, and after that, we are gonna go to the second chapter, which is fluid statics.